In 1978, NASA scientist Donald Kessler proposed a scenario. If the density of objects in low Earth orbit reaches a critical threshold, a single collision produces debris. That debris collides with other objects. Those collisions produce more debris, which collides with more objects. A cascade, self-sustaining, unstoppable. The result, a permanent shell of hypervelocity shrapnel surrounding the Earth, making it impossible to launch anything into space or maintain anything already there. For decades, possibly centuries, Donald Kessler called it an ablation cascade. Everyone else calls it Kessler syndrome. It has not happened yet. It is March 14th, 2031. The crew of the orbital maintenance vessel, Meridian, are on day 11 of a 14-day mission. 3 crew members. Mission Commander Rosa Ferreira, 12 years experience, 2 previous long-duration missions, the kind of calm that only comes from having been afraid, and handled it more than once. Flight Engineer Thomas Kwan, structural specialist, the person you want when something needs to be fixed, fast, with whatever is available. Systems Officer Dr. Yemi Briggs, communications and navigation, the quietest member of the crew, and the first one to notice when something is wrong. Their mission, routine maintenance on the Helios 7 weather satellite, replacing a degraded solar panel array. A job they have done variations of, 17 times between them. Routine. Day 11 of 14. Almost done. At 14:33 station time, a fragment of debris from the 2007 Chinese anti-satellite weapons test, a test that, in a single moment, added over 3,000 pieces of trackable debris to low Earth orbit. A fragment from that event, no larger than a pebble from a garden path, traveling at 17,500 miles per hour, struck the Meridian's port thruster housing. The crew heard nothing. In space, there is no sound. What they felt was a vibration. Sharp, brief, like someone had struck the hull, once, with a hammer. Yemi looked up from her console first. Then the alarms started. The pebble had passed clean through the thruster housing. Entry hole, 2 centimeters. Exit hole, 11 centimeters. The debris, traveling at that velocity, does not simply pierce a surface. It explodes through it, transferring energy, shattering material, sending secondary fragments in every direction from the exit point. The port thruster was gone. The fuel line feeding it was severed. And the secondary fragments, the pieces of their own ship turned into projectiles by the impact, had struck the primary communications antenna housing. They were still in contact with Houston, for now. But Tomas, looking at the damage assessment on his screen, was already doing the math on something else entirely. Something much worse than a broken thruster. The fragment that struck Meridian had not simply damaged a ship. It had itself been damaged by the impact. Split into 17 detectable pieces and an unknown number of fragments too small to track. 17 new pieces of debris, each one now on a slightly altered trajectory, each one carrying energy from the original impact, each one heading towards something else. At 14:41, 8 minutes after the initial strike, the first secondary collision occurred. A fragment from the Meridian impact struck the Cosmos 2543 defunct Russian satellite. The Cosmos 2543, traveling at 17,000 miles per hour in the opposite orbital direction, came apart. In seconds, it became 412 new pieces of debris. Tomas watched it happen on his tracking screen. A thought came through his mind, quietly. In low Earth orbit, objects travel at approximately 17,500 miles per hour. At this velocity, the kinetic energy of a 10-gram fragment is equivalent to a hand grenade. When one object is destroyed, it becomes hundreds. When hundreds collide, they become thousands. The mathematics of an ablation cascade are not linear. They are exponential. Each collision does not add debris, it multiplies it. Donald Kessler estimated that once a cascade reaches critical density, it becomes self-sustaining within hours. Not days. Hours. By 1530, 57 minutes after the initial impact, the cascade had consumed 11 satellites. By 1600, 23. By 1700, the tracking screen on the Meridian had stopped showing individual objects. There were too many. What it showed instead was a density map, a visualization of debris concentration across their orbital band. It looked like a storm system, a hurricane made of metal, moving at 17,000 miles per hour in every direction, and the Meridian was inside it. Below them, on Earth, things were beginning to go wrong. GPS signals flickering, mobile networks dropping, weather satellites going dark, one by one. The meteorologists watching their screens with the particular alarm of people who understood exactly what they were losing and exactly what that means. A cargo ship in the Pacific, losing navigation. Aircraft being rerouted as air traffic control lost satellite contact, sector by sector. The internet slowing. Then, for large parts of the world, stopping. The world below did not yet understand what was happening above it. They just knew that everything was going wrong at once. Commander Ferreira had 3 problems, in order of urgency. First, the Meridian's port thruster was gone. Without it, they could not execute a standard deorbit burn. They did not have enough thrust from the remaining thrusters to bring the ship down safely on the standard trajectory. Second, the communications antenna was degraded. Their signal to Houston was weakening. Every debris strike on the hull, and there had been 19 of them in the past hour, risked taking it out entirely. Third, the cascade was still growing. Every hour they stayed in orbit, the debris density increased. Every hour they stayed, the chance of a catastrophic hull breach increased with it. They could not stay. They could not leave. Not in the normal way, at least. Rosa Ferreira floated to the center of the crew module and looked at her 2 crew members and said, "We are going to do this the old way." The old way meant this. No digital navigation, no computer-assisted burn calculation, no GPS guidance for re-entry. Tomas pulled out a physical manual, an actual printed document in a waterproof binder, clipped to the wall of the crew module, and began calculating by hand the deorbit burn parameters. Pencil, paper, math. Yemi switched the communications system to its lowest power analog backup, a system so simple, so stripped down, that it used a transmission frequency the cascade debris could not affect, because it was the same frequency used by ships in 1960s. And Rosa, using a mechanical thruster control panel, physical switches and valves, no software between her hand and the engine, began preparing the ship for the burn. Outside the hull, the debris hurricane raged. Every few minutes, something struck them. A shudder, a vibration, that they felt through the structure of the ship, in their hands and their feet and their chests. Tomas did not look up from his calculations. Yemi did not look up from her analog console. Rosa did not look up from the thruster panel. They worked. At 1914, 4 hours and 41 minutes after a pebble struck their ship, Commander Rosa Ferreira threw 3 physical switches in sequence and fired the remaining thrusters on a manually calculated burn aimed at a re-entry window that Tomas had computed on paper using orbital mechanics equations that had not changed since the 1960s. The burn lasted 47 seconds. It was not perfect. The trajectory was not the one the computer would have chosen. The re-entry angle was steeper than nominal. The landing zone was 600 kilometers from the intended target. But it was within survivable parameters. Just barely. They hit the atmosphere at 1931. The heat shield did its job. The parachutes deployed. At 1944, the Meridian Crew module struck the surface of the North Atlantic Ocean at a velocity that was uncomfortable but survivable, and nothing else mattered. All 3 crew members were recovered 4 hours later by a Coast Guard vessel that had navigated to their position using paper charts and a magnetic compass. Because by then, there was nothing else left to navigate with. In the days that followed, the world learned what it had lost. Not dramatically, not all at once, slowly, in the particular way that you only notice how much you depended on something after it is gone. Farmers who had used GPS-guided equipment for 20 years drove their tractors manually across fields they had to relearn by eye. Shipping companies rerouted their fleets using radio navigation systems that most of their crew members had never been trained on. Weather forecasting became a guess. The financial systems that depended on satellite-synchronized timing signals to coordinate global transactions went into emergency manual protocols that nobody had tested in 15 years. Mobile phones still worked. For calls within range of a ground tower. For everything else, the maps, the data, the instant connection to anywhere on Earth. Barely there. And above it all, in low Earth orbit, the cascade continued. Self-sustaining. Unstoppable. A hurricane of metal, circling the planet at thousands of miles per hour, consuming the last remaining satellites, one by one, until the orbital band that humanity had spent decades, years building into was empty of everything useful and full of everything dangerous. Kessler syndrome is not science fiction. Donald Kessler is a real scientist. His cascade model is real science. The 30,000 plus pieces of debris currently in orbit are real. NASA tracks them. The European Space Agency tracks them. Every spacefaring nation tracks them because they know what one pebble at thousands of miles per hour can start. We have been extraordinarily fortunate. There have been close calls, near misses, moments where a slightly different trajectory, a slightly different orbital timing might have started exactly what started in this story. GO, the International Space Station, performs debris avoidance maneuvers multiple times per year. We are not ignoring this problem, but we are not solving it fast enough either. Every satellite launched adds to the density. Every collision, however small, adds debris. Every year we wait. The threshold gets closer. The cascade does not need a disaster to start. It just needs one wrong pebble in the wrong orbit at the wrong time, traveling at blistering speeds, which is every pebble up there, right now.